Did you know that some of the world's tallest skyscrapers are not standing on solid rock, but on soil that behaves almost like wet jelly? At first glance, this sounds impossible. How can structures weighing hundreds of thousands of tons rise safely from ground that can compress, shift, and deform under pressure? One wrong move, and the entire building could tilt, crack, or even collapse. Yet, engineers around the world have mastered a remarkable technique that turns unstable ground into a rock-solid foundation. Using deep foundation piles driven tens of meters below the surface, they bypass weak soils entirely and anchor massive structures to stable strata far underground. Today, Civil Engineering Edge is diving deep literally into the fascinating engineering that allows skyscrapers to defy gravity, defy soil failure, and stand tall on some of the most challenging ground conditions on Earth. Welcome to Civil Engineering Edge, the channel where engineering theory meets real-world construction challenges. If you are a civil engineering student, a practicing professional, a real estate developer, or someone deeply curious about how modern cities rise from the ground up, you are in exactly the right place. Urban expansion has pushed skyscraper construction into coastal zones, reclaimed land, river deltas, and floodplains areas dominated by weak, compressible soils. These are locations where traditional shallow foundations simply cannot perform safely. Yet, cities like Shanghai, Dubai, Mumbai, and New York continue to grow vertically at breathtaking scales. In today's video, we break down the engineering logic, geotechnical calculations, and construction methods behind deep foundation piles. You will understand how engineers analyze soil behavior, manage settlement risks, and use heavy machinery to transfer colossal loads safely to bedrock, transforming unstable ground into a reliable platform for the world's tallest structures. The impossible site paradox. At first glance, constructing a skyscraper on soft soil appears to defy basic engineering intuition. Soft clay, silt, and loose sand lack the strength and stiffness required to support enormous vertical loads. These soils compress easily under pressure, lose strength when saturated with water, and deform slowly over time. Yet modern urban development frequently demands skyscrapers in exactly these conditions: coastal cities, reclaimed land, and river basins where firm rock may lie 30 to 60 meters below the surface. This contradiction is what engineers call the impossible site paradox. On one hand, architectural ambition and economic necessity demand tall, slender buildings. On the other, the ground beneath is fundamentally incapable of supporting such loads directly. Ignoring this paradox leads to excessive settlement, structural cracking, tilting, and long-term serviceability failure. Civil engineers resolve this paradox not by strengthening the weak soil at the surface, but by strategically bypassing it altogether. Through deep foundation systems, loads are transferred past compressible layers into dense sand, stiff clay, or bedrock. This approach transforms an otherwise unsuitable site into a viable construction zone, enabling skyscrapers to rise safely where shallow foundations would fail catastrophically. Vertical loads versus compressible soils. A modern 100-story skyscraper can impose vertical loads exceeding 800,000 to 1 million tons when dead loads, live loads, wind effects, and seismic forces are combined. These forces are concentrated through columns and core walls into relatively small foundation areas. In contrast, soft coastal soils such as marine clay and silty deposits have low bearing capacity, high compressibility, and slow consolidation behavior. When such massive loads are applied to compressible soil, the soil particles rearrange, expel pore water, and compress over time. This results in long-term settlement, sometimes continuing for decades. Even if the soil does not fail immediately, gradual compression can cause uneven floor levels, cracked walls, and misaligned structural components. The challenge intensifies in high-rise buildings where load intensity increases exponentially with height. Unlike low-rise structures, skyscrapers generate extreme stress concentrations at the foundation level. Soft soils simply cannot distribute these differential settlement, the hidden structural killer. One of the most dangerous risks when building on soft soil is differential settlement. Unlike uniform settlement where the entire structure sinks evenly, differential settlement occurs when different parts of the foundation settle by different amounts. This uneven movement induces internal stresses that structures are not designed to resist. In skyscrapers, even a few millimeters of differential settlement can have severe consequences. Columns may experience additional bending, shear walls can crack, and floor slabs may distort. Over time, these stresses propagate upward, leading to facade damage, malfunctioning elevators, jammed doors, and compromised structural integrity. In extreme cases, differential settlement can lead to partial or total structural failure. Soft soils amplify this risk because their properties vary significantly across short distances. Changes in moisture content, soil thickness, or consolidation rate can cause uneven load response beneath the same building. Without proper foundation design, one corner of a tower may settle faster than another, causing dangerous tilting. Engineers must therefore design foundations not just for strength, but for settlement control. Eliminating or minimizing differential settlement is often more critical than achieving adequate bearing capacity, making deep foundation piles an essential solution rather than an optional one. Deep foundation piles, the engineering solution. Deep foundation piles provide a direct and reliable solution to the challenges posed by soft soil. Instead of relying on weak surface layers, piles transfer structural loads to deeper, stronger strata through end bearing, skin friction, or a combination of both. These piles act as vertical structural elements that bypass compressible soil and anchor the building to stable ground. End-bearing piles transfer loads directly onto hard strata such as dense sand or bedrock, functioning like columns embedded in the earth. Friction piles, on the other hand, distribute loads along their length through shear resistance between the pile's surface and surrounding soil. In most skyscraper projects, engineers use a hybrid approach to optimize performance and safety. Modern piles can extend 30 to 80 meters below ground, constructed using reinforced concrete, steel, or composite materials. Advanced geotechnical analysis determines pile diameter, spacing, length, and load capacity with precision. Heavy machinery such as rotary drilling rigs, hydraulic hammers, and continuous flight augers are employed to install these piles with millimeter-level accuracy. By using deep foundation piles, engineers transform unstable, weak soil conditions into dependable load-bearing systems, making it possible for skyscrapers to rise safely where conventional foundations would never survive. Mapping the invisible underground. Before a single pile is drilled or driven into the ground, engineers must first understand what cannot be seen. The soil beneath a proposed skyscraper site is not uniform, predictable, or forgiving. It is a layered, complex system shaped by geological time, water movement, and human intervention. Mapping this invisible underground accurately is the foundation of safe high-rise design. A single incorrect assumption about soil depth, stiffness, or strength can result in catastrophic settlement, pile failure, or excessive construction costs. This is why modern foundation engineering relies on advanced subsurface investigation techniques that go far beyond traditional boreholes. Engineers combine field testing, laboratory analysis, and digital modeling to create a three-dimensional understanding of soil behavior beneath the site. This underground map allows engineers to predict how loads will travel from the building into the ground, how soil layers will interact with foundation elements, and where stable strata capable of supporting extreme loads actually exist. In skyscraper projects, this process transforms uncertainty into data-driven engineering decisions, ensuring that every pile is designed, placed, and constructed with precision. Advanced 3D geological modeling and seismic CPT testing. Modern skyscraper foundations depend heavily on three-dimensional geological modeling combined with advanced in-situ testing methods such as seismic cone penetration tests, SCPT. Unlike conventional boreholes that provide information only at discrete points, 3D modeling integrates data across the entire site, creating a continuous subsurface profile. This allows engineers to visualize soil layers, bedrock contours, groundwater conditions, and weak zones with remarkable accuracy. Seismic CPT testing plays a critical role in this process. As the cone penetrometer is pushed into the ground at a controlled rate, it measures cone resistance, sleeve friction, and pore water pressure. Simultaneously, seismic sensors record shear wave velocity, which directly correlates with soil stiffness and elastic properties. This data enables engineers to estimate bearing capacity, settlement potential, and dynamic response under seismic and wind loading. When combined with GPS positioning and real-time digital logging, SCPT data can locate bedrock depth with millimeter-level precision. This is crucial for determining pile termination levels, especially in sites where bedrock undulates or dips sharply. By integrating borehole logs, laboratory test results, and SCPT data into 3D geological software, engineers create a reliable digital ground model. This model becomes the backbone of foundation design, reducing uncertainty, optimizing pile length, and preventing costly design revisions during construction. Soil composition and its influence on pile selection. Soil composition fundamentally governs how foundation piles behave under load. One of the most critical design decisions engineers make is selecting the appropriate pile type based on whether the soil is cohesive, such as clay, or granular, such as sand. Each soil type interacts with piles in dramatically different ways. Cohesive soils like clay derive their strength from electrochemical bonding between particles. These soils can sustain load even without confinement, but are highly sensitive to moisture content and consolidation time. In clay-dominated sites, friction piles are often favored because they mobilize shear resistance along the pile shaft. However, engineers must carefully evaluate long-term consolidation effects, as clay may continue to compress long after construction, reducing effective skin friction over time. Granular soils such as sand, on the other hand, rely on particle interlocking and friction for strength. These soils typically exhibit higher immediate bearing capacity and lower long-term settlement. In sandy strata, piles benefit significantly from both shaft friction and end-bearing resistance, especially when embedded into dense sand layers. Driven piles often perform well in granular soils because driving increases soil density around the pile, enhancing load capacity. Understanding these differences allows engineers to tailor pile material, installation method, diameter, and length to soil behavior, ensuring optimal performance while minimizing construction risks and costs. Skin friction versus end-bearing capacity calculations. One of the most critical analytical steps in deep foundation design is calculating the balance between total skin friction capacity and end-bearing resistance for the building footprint. This calculation determines whether piles will primarily act as friction piles, end-bearing piles, or a combination of both. Skin friction capacity is calculated by integrating the shear resistance developed along the pile shaft across each soil layer. Engineers consider soil type, effective stress, pile surface roughness, and adhesion factors. In layered soil profiles, shaft resistance varies significantly with depth, requiring detailed stratified analysis rather than a single average value. End-bearing resistance, by contrast, depends on the strength and stiffness of the soil or rock at the pile tip. For piles terminating in bedrock or dense sand, end-bearing can carry a substantial portion of the load. Engineers calculate this using bearing capacity theories adapted for deep foundations, incorporating safety factors to account for construction tolerances and soil variability. For a given skyscraper footprint, engineers analyze load distribution across hundreds or even thousands of piles. The objective is to ensure uniform load sharing, minimize differential settlement, and maintain acceptable factor of safety. Advanced software simulates load transfer mechanisms and predicts pile behavior under service and ultimate loads. This precise balance between skin friction and end-bearing resistance is what transforms an unstable site into a structurally reliable foundation system. Forging the deep support system. Once the subsurface conditions are fully mapped and the foundation design is finalized, the project moves into its most physically demanding phase, installing the deep support system. This is where engineering calculations are transformed into real-world structural resistance. Deep foundation piles must be constructed and installed with extreme precision, often through highly saturated, unstable soil layers, while maintaining strict vertical alignment and load capacity requirements. In high-rise projects, piles are not minor structural elements. They are massive load-bearing members designed to carry thousands of kilonewtons each. Any deviation in installation depth, inclination, or material integrity can compromise the entire foundation system. Engineers therefore rely on specialized heavy machinery, advanced installation techniques, and continuous quality control to ensure performance matches design intent. This phase represents a controlled battle between machine power and ground resistance, where every meter of penetration is monitored, verified, and documented. Forging this deep support system is what ultimately allows skyscrapers to rise safely from ground that would otherwise be incapable of supporting them. Heavy machinery driving piles through saturated soil, driving massive concrete and steel piles through more than 100 meters of saturated soil demands machinery of extraordinary power and stability. The backbone of this operation is the pile driving rig, often mounted on crawler cranes capable of lifting loads exceeding several hundred tons. These rigs are designed to maintain vertical accuracy while resisting lateral forces caused by soft, waterlogged ground. For precast concrete piles and steel H-piles, hydraulic and diesel hammers are commonly used. These hammers deliver repeated high-energy impacts, forcing the pile downward through layers of clay, silt, sand, and fill material. In extremely deep installations, segmental piles are welded or coupled on-site as penetration progresses. Bored pile construction relies on rotary drilling rigs equipped with high-torque power heads. These machines drill through saturated soil using augers, buckets, or core barrels, while temporary casing or drilling fluids stabilize the borehole. Once the required depth is achieved, reinforcement cages are lowered, and high-strength concrete is poured using TREMI methods to prevent segregation. Operating in saturated soil introduces challenges such as borehole collapse, groundwater inflow, and loss of bearing capacity during installation. Engineers counter these risks through controlled drilling rates, casing systems, and continuous monitoring, ensuring each pile reaches its designed depth and capacity safely. Diesel hammer driving versus vibration-based installation. Pile installation methods must balance efficiency, safety, and environmental impact, especially in dense urban environments. Diesel hammer pile driving is one of the fastest and most energy-efficient methods for installing driven piles. Diesel hammers deliver high-impact blows, allowing piles to penetrate dense soils rapidly. This method is particularly effective in granular soils where soil densification around the pile increases load capacity. However, diesel hammer driving generates intense noise and ground vibrations. In urban areas, this can damage nearby structures, disturb residents, and interfere with sensitive infrastructure such as underground utilities and metro tunnels. For this reason, alternative installation methods are increasingly preferred in cities. Vibratory pile driving and pressing systems use high-frequency oscillations to reduce soil resistance around the pile, allowing it to sink under its own weight or with minimal downward force. These systems produce significantly less noise and vibration compared to impact hammers. Hydraulic press-in methods, in particular, are ideal for urban sites where vibration limits are strictly regulated. While vibration-based methods are quieter, they may not be suitable for all soil types or extreme depths. Engineers carefully evaluate soil behavior, pile length, and load requirements before selecting the appropriate installation technique, often combining methods across a single project to optimize performance and compliance. Real-time monitoring during pile installation. Modern deep foundation construction relies heavily on real-time monitoring technology to ensure pile performance meets design specifications. As piles are driven or bored into the ground, engineers continuously measure penetration resistance, energy transfer, and structural integrity. This data-driven approach eliminates guesswork and significantly reduces construction risk. For driven piles, pile driving analyzers (PDA) are attached to the pile head. These instruments record stress waves generated during hammer impacts, allowing engineers to estimate bearing capacity, detect pile damage, and verify hammer efficiency. The data is transmitted instantly to on-site engineers, enabling immediate adjustments to driving, energy, or technique. In bored pile construction, sensors monitor drilling torque, penetration rate, slurry density, and concrete volume. Any anomaly such as sudden loss of resistance or excessive soil inflow triggers immediate corrective action. Reinforcement cage alignment and concrete integrity are also verified using ultrasonic and cross-hole sonic logging after installation. These monitoring systems create a digital record for every pile, documenting compliance with design assumptions and safety factors. By combining instrumentation with engineering judgment, real-time monitoring ensures that each pile contributes reliably to the foundation system, forming a deep support network capable of sustaining skyscrapers for generations. Securing the structural base. After hundreds or even thousands of deep foundation piles have been installed and verified, the focus shifts to integrating these hidden structural elements into a single, unified system. This phase is where underground engineering meets visible construction. The objective is not only to support vertical loads, but also to manage lateral forces from wind, seismic activity, and long-term soil movement. The structural base must behave as a rigid, stable platform that distributes loads evenly while preventing differential settlement. Engineers achieve this through carefully designed pile caps, extensive load testing programs, and seamless integration with the building's core structure. Any weakness at this stage compromises the performance of everything built above it. Securing the structural base is therefore one of the most critical milestones in skyscraper construction, transforming a collection of individual piles into a coordinated foundation system capable of supporting extreme loads for decades. Engineering the pile cap, the load distributor. The pile cap is the structural element that unifies individual deep foundation piles into a single load-bearing system. Typically constructed as a massive reinforced concrete raft, the pile cap distributes loads from columns, shear walls, and the building core across multiple piles simultaneously. Without a properly designed pile cap, even the strongest piles cannot function effectively as a foundation system. From an engineering standpoint, the pile cap must resist bending, punching shear, and torsion generated by uneven load distribution. Its thickness often ranges from 1.5 to 4 meters in skyscraper projects, reinforced with dense layers of high-strength steel arranged in both orthogonal and diagonal patterns. The design ensures that stresses are spread uniformly, preventing overloading of individual piles. Pile caps also play a critical role in lateral load resistance. During wind or seismic events, lateral forces are transferred through the superstructure into the pile cap, which then distributes them into the pile group and surrounding soil. Engineers carefully model this interaction using finite element analysis to ensure structural continuity and redundancy. Construction of the pile cap demands precise coordination, accurate pile head trimming, proper reinforcement placement, and controlled concrete pouring. Once completed, the pile cap becomes the invisible platform upon which the entire skyscraper safely stands. Load testing, proving the foundation beyond design loads. Before construction can proceed upward, engineers must prove that the deep foundation system can safely carry the required loads. This verification occurs during the pile load testing phase, one of the most critical quality assurance steps in foundation engineering. Using hydraulic jacks, engineers apply controlled vertical loads to selected test piles. These loads often exceed the building's projected service load by 1.5 to 2 times, ensuring a robust margin of safety. The reaction force is provided by anchor piles or massive steel reaction frames installed specifically for testing purposes. During testing, precise instruments measure settlement, rebound, and creep behavior under sustained loading. Engineers closely analyze load settlement curves to confirm that pile behavior aligns with design assumptions. Any excessive displacement or non-linear response indicates potential issues that must be addressed before construction continues. Load testing not only verifies pile capacity, but also validates soil parameters used in design. In many cases, test results allow engineers to optimize pile length or spacing, reducing construction costs without compromising safety. This phase transforms theoretical calculations into proven structural performance, ensuring the foundation is not just adequate on paper, but reliable in reality. From underground forces to rising structural core, with the foundation system verified and secured, the project transitions from underground engineering to vertical construction. The forces generated by the building dead loads, live loads, wind pressures, and seismic effects now have a clear, continuous load path into the earth. The pile cap connects directly to the building's core walls and primary columns, forming the base of the structural skeleton. As the reinforced concrete core begins to rise, it carries the accumulated loads downward through the pile cap into the deep foundation system. This seamless transition ensures that dynamic forces are distributed efficiently without inducing localized stress concentrations. From a visual perspective, this is the moment when a project truly comes alive. What was once a hidden network of piles and reinforcement now supports visible structural elements climbing skyward. Engineers continue to monitor settlement and alignment during this phase, ensuring that the superstructure behaves as predicted. This transition marks the success of the foundation design. The invisible dynamics of soil-pile interaction are now supporting a growing skyscraper, demonstrating how precise engineering beneath the surface makes architectural ambition possible above ground. Engineering stability for a rising skyline. Modern skylines are no longer limited by surface conditions. What were once considered impossible construction zones, soft clay coastlines, reclaimed land, river deltas, and marshy waterfronts have become the most valuable urban real estate in the world. This transformation is not driven by architecture alone, but by advances in deep foundation engineering that allow skyscrapers to stand safely on unstable ground. By transferring massive structural loads to deep, competent strata, engineers have eliminated the traditional limitations imposed by weak soils. Deep foundation systems now form the backbone of urban expansion, enabling cities to grow vertically while maximizing limited land resources. As we move into 2026 and beyond, foundation engineering continues to evolve, supporting taller, slimmer, and more complex structures than ever before. This section explores how modern deep foundation systems have reshaped urban development, where the future of this technology is headed, and why the true strength of a skyscraper remains hidden beneath the surface. From unbuildable waterfronts to prime urban real estate, only a few decades ago, waterfront sites dominated by soft marine clay and loose silts were considered unsuitable for high-rise construction. Excessive settlement, liquefaction risk, and long-term instability made these locations economically and structurally unviable. Today, using 2026 construction standards, these same sites host some of the world's most iconic skylines. Deep foundation piles have enabled this transformation by bypassing weak surface soils and anchoring structures into dense sand layers or bedrock. Modern design codes now integrate advanced soil structure interaction models, allowing engineers to accurately predict settlement behavior over the entire lifespan of a building. High-capacity board piles, diaphragm walls, and piled raft foundations are routinely used in waterfront developments. These technologies have unlocked immense economic value. Former industrial docks and reclaimed coastal zones have become hubs for finance, tourism, and residential development. Cities maximize land use while maintaining structural safety and long-term performance. By combining geotechnical science, structural engineering, and real-time monitoring, deep foundations have redefined what is buildable, turning unstable ground into the foundation of modern urban growth. The future of foundation technology. The future of deep foundation engineering is being shaped by innovation at the material, analytical, and digital levels. One of the most promising developments is self-healing concrete, which uses microcapsules or bacteria-based systems to automatically seal cracks in deep piles and pile caps. This technology enhances durability by preventing water ingress and corrosion, critical for foundations exposed to groundwater and marine environments. Artificial intelligence is also transforming foundation design. AI-driven algorithms analyze vast geotechnical datasets to optimize pile layout, spacing, and depth. These systems can generate designs that reduce material usage while maintaining safety, resulting in faster construction and lower carbon footprints. Advanced sensors embedded within piles now provide continuous performance data, allowing engineers to monitor load distribution and settlement throughout the building's life. This shift from reactive maintenance to predictive performance management represents a major leap forward. Together, these technologies are redefining deep foundation systems not just as static structural elements, but as intelligent, adaptive components of future skyscrapers, where true strength really lies. When people admire a skyscraper, they look upward toward glass facades, elegant forms, and record breaking heights. But from an engineering perspective, the true strength of a skyscraper lies far below the surface. It exists in the deep foundation piles, silently transferring loads into the earth, resisting settlement, and stabilizing the structure against nature's forces. No matter how advanced the superstructure design may be, it is only as reliable as the foundation beneath it. Deep foundation systems provide continuity, redundancy, and resilience, ensuring that wind, seismic forces, and time itself do not compromise structural safety. These unseen systems represent the highest level of engineering responsibility. They are designed not for visibility, but for permanence. Every successful skyscraper stands as proof that when the ground is weak, engineering becomes stronger, solving problems where failure is not an option. A true best example, Burj Khalifa Foundation System. The Burj Khalifa in Dubai stands as the ultimate example of deep foundation engineering on challenging ground. built on weak, carbonate-based soils with high ground water levels, the world's tallest building relies on a deep foundation system of 190 high-capacity board piles, each extending approximately 50 meters into the ground. These piles work primarily through skin friction, supported by a massive reinforced concrete pile raft over 3.7 meters thick. Engineers conducted extensive load testing to validate long-term settlement performance under extreme loads. Advanced monitoring systems tracked foundation behavior throughout construction and after completion. Without this meticulously engineered deep foundation system, constructing an 828-meter-tall tower on such soil would have been impossible. The Burj Khalifa proves that height is not limited by ground conditions, but by the precision of engineering beneath the surface. Skyscrapers may define a city's skyline, but their survival depends on what lies beneath. Deep foundation engineering is the silent force that transforms unstable soil into a platform for human ambition. Every pile driven, every test performed, and every calculation made ensures that these giants of steel and concrete stand strong for generations. At Civil Engineering Edge, we believe the most fascinating engineering stories are the ones you cannot see. If this video expanded your understanding of how skyscrapers defy gravity on soft ground, make sure to like, share, and subscribe. Join us as we continue exploring the hidden engineering that shapes our world from the depths of the earth to the heights of modern skylines. Because true engineering excellence is built from the ground up.